Hello again. I'm here for my final presentation for Math 312, spring of 2015 at FSU. My name is Michael Diaz, and I'm going to be talking about the Chinese remainder theorem today. So, let's start with the history of the Chinese remainder theorem. Where did it come from? The Chinese remainder theorem came from China sometime in the 1st century AD. I read several things that some scholars refer to it as actually being established as the Chinese remainder theorem in the 4th century AD, but the majority of the scholarly work that I found, one in particular was Jane Liu from New York University, expressed that it was actually formally called the Chinese remainder theorem in the 1st century AD. So we'll go with that. Next is, who came up with the theorem? So there was a mathematician by the name of Sun Tzu who published a book, and here's the English translation of that book, The Arithmetical Classic of Sun Tzu. In his book, Sun Tzu introduced a method for solving systems of linear congruences that was eventually called the Chinese remainder theorem. However, I'll discuss that in the proof and so forth in the conclusion. So, you might be asking, what is the Chinese remainder theorem? But let's back up for a second. We need to understand a few of the background things before we can talk about what the Chinese remainder theorem is. First, to understand how the Chinese remainder theorem works, I'm going to discuss 5 concepts that should be mentioned. So the first is the mod operator. The mod operator, which is used to mathematically define the Chinese remainder theorem, is the same as in many programming languages, modulo percent operator. And this would be just like this in many computer types and programming languages. So with that background, moving on to the second concept, in modular arithmetic, if A mod B equals B mod A, get rid of this. Then we can express this as so if A mod B is equal to B mod A, then we can express this as A, and this 3 lines here, it's not equals, it's congruent. So A is congruent to B mod M, where M is always greater than 1. It's always positive. And we're speaking in integers here, always integers. A, B, and M are always integers when dealing with the Chinese remainder theorem. So M is always a positive integer, and A and B are always integers, like I just said. If we don't have integers to deal with, then we don't have Chinese remainder theorem. So this sort of moves on. So knowing that our modulus is greater than 1 and A and B are always integers, then we can come to the form of a linear congruence as a congruence in the form of A times X is congruent to B mod N. And like before, just like N is greater than 1. X represents our variable. And A and B are positive integers. So two numbers. So two numbers are considered relatively prime, and I'll be using the uptack symbol to indicate that two numbers are relatively prime, or co-prime. So two numbers are considered to be relatively prime or co-prime if their GCD is equal to 1, just like if A and B are equal to 1, then they're relatively prime to one another. So a list of numbers can be considered pairwise relatively prime. That is, if they have no common positive divisors other than 1. For example, if we look at the set, it's more like another 3 there. Then if we look at this set, the set here is pairwise relatively prime, even though individually some of the numbers are composite numbers, but we look at them as pairs within the set, right? And as we look at them as sets of A and B, if we take their GCD as pairs within the set, they're equal to 1. Therefore, the set is pairwise relatively prime. So, the last concept I want to talk about, and I know you probably know what where it is the Chinese remainder theorem already, is if A and N are relatively prime, so A is uptack to N, and N is greater than 1, N is greater than 1, then an inverse of A mod N exists. So then A mod N exists. Furthermore, the inverse of this unique mod N, furthermore, the inverse of A mod N, since it exists, it's unique to mod N. That is, there's a unique positive integer A bar, we'll say, that exists because it's unique because A mod N exists. So, with that being said, a unique positive integer A bar, and A bar, since this unique value exists, it is less than N. So A bar, the inverse of A mod N, since A and N are relatively prime, N is greater than 1, then A mod N exists, you then have a unique inverse, we're just calling A bar, which is always going to be less than N. That is the inverse of A mod N, and every other inverse of A mod N is congruent to A bar mod N. Okay, that would sort of hurt my head, so hopefully you understood it a little better than me. But let's have the theorem. So with that background, now we can sort of look at what is CRT. So the Chinese theorem states that when the moduli on the system of linear congruences are pairwise relatively prime, that's what we just discussed, there's a unique solution to the system modulo the product of the moduli. Okay, so that's what it states. Well, let's look at sort of a general definition. Now, this is a general definition. I'm going to try and walk sort of through this. So, looking at the board, we have that letting lowercase n1, n2 to nr are positive integers, right? So we know that n1, n2, so forth, to nr is greater than 0. It's positive integers, such that n sub I is relatively prime to n sub j, for all I not equal to j. And like I said before, the uptack symbol is being used to indicate integers are co-prime. then the system of linear congruences can be set as x, which is just representing a number, a variable, right, is congruent to b sub 1 mod n sub 1. And following, for our second congruence, we have x, as you can see, b2 mod n2, all the way to br n r. Have simultaneous solution, which, like we said, right, we'll recall back to, it's mod the product of the moduli. So the moduli in n1, n2 to nr, right? We have that there's a unique solution from I equals 1 to r of ni. To obtain the solution to the set of congruences, then we just need to look at the following. So we can say that x is congruent to b1 times c sub 1 of capital N over n sub 1 and plus all the way to br c sub r n over nr mod n. Then here's the key, where capital N equals the sum of n1 and 2 all the way to nr, and ci is determined by taking n over ni congruent to 1 mod ni. And this will become more clear in the following example. So let's have an example. So why do we need the Chinese for linear theorem? Let's look at this following example. An old woman goes to the market with a basket of eggs. She sets the basket down and a horse accidentally steps on it, crushing all the eggs. The rider offers to pay her for the damaged eggs and asks, how many eggs did she have? She tells the rider that she can't remember, but when she had taken all the eggs out 3 at a time, there were 2 left over. So taking them out 3 at a time, a remainder of 2 left in the basket. When she took them out 5 at a time, there were a remainder of 3 left in the basket. And when she took them out 7 at a time, there were 2 left in the basket. So the question is, what's the smallest number of eggs she could have had in the basket? Well, let's take a look. So we can formulate the system of linear congruences. Excuse me, lost my train of thought. As x congruent to 2 mod 3, right? Recall that when she pulls them out 3 at a time, there's a remainder of 2. When she pulls them out 5 at a time, there's a remainder of 3. And 7 at a time, there's a remainder of 2. So now we have our system built. We just need to solve for x. So let me write this out real quick. I'm going to hope there's enough room. I'm going to write my system over here just so we can recall. So we have x is congruent to 2 mod 3. X is congruent to, I believe it was 3 mod 5. And x is congruent to 2 mod 7. So that's our system of linear congruences. So remember, recalling the definition, our n1, n2 to nr is lowercase, right? So we need to first find the product of our moduli, right? So to solve for x, we have to let n equal 3 times 5 times 7, which equals 105. This is the important number right here, 105. All right? So that's our capital N. Okay. So next, in order to find, we need to find a number that satisfies each of the 3, right? So we're looking for our CI. Okay? So we take 105 divided by the moduli of each, right? Because we're multiplying all 3 together to get a single moduli. So all the systems can be mod 105. Now we need to break them apart. So we say 105 divided by 3, and we say 105 divided by 5, and we say right over here 105 divided by 7, right? Then we see that, so by looking at this, we see that 2 is an inverse of n over 3 equals 35, right? This is our n over 3 equals 35. So keeping this in mind, we have, I gotta write this over here real quick, just to keep this in mind, equals 35. We've got 105 equal over 5 equals 21. And we've got 105 over 7 equals 15. All right? So we see that 2 is an inverse of n over 3. So we can write this as n over 3 equals 35, right? Because n is equal to, remember that n is equal to 105. So we can write this as 35 times 2, that a bar, that unique inverse, right, is congruent to 2 times 2, which is congruent to, remember, in our definition, it's congruent to in our concept that we talk about 1 mod the moduli. So we have 1 mod 3. All right? Now, 1 is an inverse, so if we solve this out, we have 1, right? Because 35 times 2 is congruent to 2 times 2. We say that 2 times 2 is 4 minus 1 equals 3 divided by 3, which gives us 1. So we now say that n over 5 equals 21 mod 5 because 21 is congruent to 1 mod 5. And we know that 20 minus 1 gives us 20 over 5, right? So, do that, excuse me, 21 gives us 20 over 5. So, that works. So, 1 is an inverse of n over 7 equals 15 mod 7, because 15 minus 1 is 14. 14 divided by 7 is 2. So, with that being said, we can now come up with a solution. So, let's look at the form of our solution. So thus the solution to the system are those x's such that, and I had to erase that to make room, we've got 2 times 35 times 1, times 2, we get 2. That was our inverse, I forgot. Plus, I erased it, it was 3 times 21 times 1, plus, I'm going to move this down here, 2 times 15 times 1. And that's what we just solved on the previous. So, multiplying, doing the general arithmetic, we get that this is 233 congruent to 23 mod 105. You might ask, okay, how did we get that? Well, you just take 233 and divide it by the modulus. You then have, so you get 233 over 105 equals 2.1904 ... You then take away that 2, and we're looking at the remainder. And you multiply this remainder back times the moduli of 105, which gives you 23, your remainder. Thus, we can see from the slide that the final answer is 23x. And we have that was the smallest amount that could have been in the bathroom. So, in conclusion, what did we talk about? We talked about when the Chinese predictor theorem came about. We talked about who came up with it. We gave some concepts to understanding what the Chinese remainder theorem is. We then gave a general definition, and we looked at it at applying that definition to an example. So I just want to leave you with this. The Chinese remainder theorem seems to have been known throughout Asia since the arithmetical classic of Sun Tzu first appeared in the 1st century AD. Although Sun Tzu did not provide a complete proof, mathematicians in India, such as Aryabhata, which we talked about previously in this course, went on to provide a complete algorithm for solving this problem. Finally, it's amazing to see how ancient mathematics, like Chinese remainder theorem and Euclidean algebra, I make that reference to Euclidean algorithm because in the paper I wrote on this topic, there's a large reference and usage of Euclidean algebra, continue to find so many applications today. And I just want to point out a couple of those applications are coding theory. That was that reference in the very beginning, the first concept of the modulo operator, modulo percent operator being used in many programming languages. On top of that, they're used in RSA. The Chinese remainder theorem and the likes is used in RSA cryptography and several other theoretical mathematical fields. But there are more and more applications becoming known and relevant today with Chinese remainder theorem because of technology and the ever-growing expansion